How fast the stator poles alternate and the rotor poles turn depends on the frequency of the alternating current. Most AC is either 50 or 60 hertz, which means that it makes one complete AC cycle going from 0 to positive to negative to 0 again, either 50 or 60 times a second. So powered by 60 hertz AC, the poles will alternate from north to south and back to north again 60 times a second. In a two-pole single-phase motor like this, each rotor pole must go from one stator pole past the next exactly as the polarity reverses and continue on to the next in time for the reversal there. In other words, the rotor poles must make one complete revolution every AC cycle to stay synchronized with the stator pole reversals. They will turn at 60 cycles per second times 60 seconds, or 3,600 revolutions per minute. So the synchronous speed of a motor depends on the frequency of the AC. But it also depends on the number of poles in the motor. In a four-pole motor, each rotor pole must move from one stator pole past the next and on to the next for every AC cycle. The rotor poles must make half a complete turn, and the synchronous speed of the motor will be half that of a two-pole motor. As a result, the synchronous speed of any motor in RPM equals the frequency in hertz times 60 seconds per minute divided by half the number of poles. A four-pole motor powered by 60 hertz AC has a synchronous speed of 60 times 60 divided by 2, or 1,800 RPM. An AC motor which can run at more than one fixed speed makes use of this principle. When you set it to run on a different speed, the switch connects the individual windings in the motor for a different number of poles. For maximum speed, the motor is connected for the fewest number of poles. Reconnecting the windings for twice as many poles cuts the speed in half. 3 times as many poles produce 1/3 the speed, and so on. When you wire up a multiple speed motor for one of its speeds, you are doing the same thing, connecting the individual winding leads together to provide a certain number of stator poles. Now let's look at the situation where the alternating current is three-phase. There are 3 power lines, and in a two-pole motor, each of them is connected to a set of coils producing 2 poles. The currents in the 3 power lines are phased so that the magnetic poles on the stator actually appear to rotate around the motor. As current comes in phase A, it flows through the phase A coils to produce a north pole on one side of the motor and a south pole on the other. At the same time, current in phases B and C is negative and produces south and north poles as shown. So one side of the motor is north and the other is south. Shortly after phase A's peak, however, current reverses in phase B and produces a north and south pole. The poles have shifted around the motor. Soon after that, the current has reversed in phase A, followed by phase C. Each time the current in any phase reverses, the stator's poles move 1/6 of the way around the motor. Since there are 3 phases and they all reverse twice in each AC cycle, the stator poles in the 3-phase motor rotate at the synchronous speed of the motor. Now there are 2 basic types of single-phase and 3-phase AC motors: induction motors and synchronous motors. They differ in the way the rotor poles are produced. In induction motors, the rotor poles are the result of currents induced in rotor conductors. Look at the rotor closely. Often, all you'll see is a round core of laminated steel. But notice the aluminum rings on both ends. They are not there just to hold the fan blades, which are usually cast as part of the rings. If you could look inside the iron core, you would see that the rings are connected by solid bars through holes in the core. The bars and the end rings form a conductive cage, often called a squirrel cage. The cage is often cast in place, though sometimes it is assembled from separate copper bars and rings. Now, anytime lines of magnetic flux move through a conductor, voltage is induced in the conductor. The more lines, and the faster they move, the higher the induced voltage. At startup, as soon as alternating current is switched on to the stator windings, magnetic poles travel around the rotor at synchronous speed. The rotating flux lines sweep past the stationary rotor conductor bars rapidly and induce maximum voltage in them. Resistance is low, and high currents flow in the conductors. These rotor currents produce strong rotor poles, which follow around the motor between the stator poles. Each rotor pole is pushed by the stator pole behind it and pulled by the stator pole ahead of it. So the motor exerts torque. Now, as the rotor starts to turn and come up to speed, the relative motion between its conductors and the stator's rotating flux decreases. Less current is induced in the rotor. The motor exerts less torque. An induction motor can never reach exactly synchronous speed. If the conductors were turning as fast as the stator poles, no current at all would be induced in the rotor, and the motor could not exert enough torque to overcome its own internal friction. Most induction motors have a no-load speed just slightly below synchronous speed. The current an induction motor draws from the lines depends roughly on the current induced in its rotor. This is because an induction motor is a kind of transformer, with the stator windings as the primary and the rotor cage as the secondary. In all transformers, primary and secondary currents are directly related. High rotor current means high stator current, strong rotor and stator poles, and a lot of torque to either drive a large load or accelerate a motor up to speed. When the motor is running at full speed, the rotor is turning almost as fast as the magnetic flux. Rotor current is considerably lower. So stator current, the current drawn by the motor, will also be low. Now, while it is true that the faster an induction motor turns, the less current it will draw, the relationship between torque and speed is not as simple. The actual torque curve for a typical induction motor looks like this. At every speed below no-load speed, an induction motor will exert a particular amount of torque. At the motor's rated speed, usually 90 to 97% of synchronous speed, the torque it exerts is enough to provide the motor's rated horsepower output. But if the motor is running slower because of a heavy load, it will produce more torque, up to a limit. In most induction motors, torque reaches a maximum called breakdown torque, when the motor is running between 70 and 90% of synchronous speed. If the load increases any more, the motor will stall suddenly, because it cannot slow down any further to produce more torque. Induction motors are especially likely to stall if line voltage is a little low. A line voltage drop of only 20% can reduce breakdown torque so much that the motor will stall even with its normal load. When the motor is stalled, it exerts the same amount of torque that it exerts trying to start its load. On almost all motors, startup torque is greater than full load torque. That means that most motors can start and run under overload conditions. However, they will not reach rated speed, and that can be damaging, because below rated speed, a motor is drawing too much current. If it is stalled or runs too slowly for too long, it will overheat, and the insulation will be damaged. The overload breakers are supposed to protect the motor by tripping, but do not rely on them completely. If you suspect that a motor is overloaded, check its speed or the current to it. Three-phase squirrel cage induction motors are more common than any other motor type in most industries because they are simple and rugged. There are no commutators, brushes, capacitors, or other components to go bad or need maintenance, and no rotor windings to short out or open. Synchronous motors are the other main type of AC motor. Compared to induction motors, most synchronous motors are slightly more complicated because power must be sent to the rotor to produce rotor poles. But synchronous motors have some advantages. They are efficient and relatively insensitive to line voltage variations. And in some applications where different operations must be exactly synchronized, these motors have an obvious advantage. They run at exactly synchronous speed even when the load varies. In a synchronous motor, the rotor poles are not produced by induction. Instead, the rotor is either a permanent magnet or, more often, an electromagnet with its own source of direct current and its own poles. When the motor is running at synchronous speed, the rotor poles and the rotor are locked into step with the rotating stator poles. Direct current for the rotor coils often comes from a controller outside the motor. A rectifier in the controller takes AC line voltage and turns it into DC. Brushes riding on slip rings in the motor conduct the DC to the rotor. You'll never find a purely synchronous motor. The reason is that it would only be able to run at synchronous speed. The motor would not be able to start itself. And even if you could get it started, if the load became too great and the rotor poles could not hang on to the stator poles, the rotor would drop out of synchronous speed. Practically any synchronous motor you are likely to find will have a partial squirrel cage built into the rotor, however, which allows it to start and accelerate as an induction motor. When it is nearly up to synchronous speed, the rotor poles lock into the stator poles. If the motor ever drops out of synchronous speed, it becomes an induction motor again. But the cage is intended for starting only. The motor will draw high current and overheat if it does not pull into synchronous speed fairly quickly. If you find a synchronous motor running below synchronous speed, the motor may be overloaded. The stator windings, rotor windings, brushes, or rotor supply may be bad. If the problem continues, the motor will burn out. So far, we've been looking at three-phase AC motors. We have seen how induction motors start up and run on three-phase power, and why a synchronous motor needs to start as an induction motor. When the AC is single-phase instead of three-phase, even induction motors cannot start themselves without special provisions. The problem is that with single-phase power, the stator poles alternate back and forth but do not actually rotate around the motor in a definite direction. So at startup, the rotor poles are pulled one way and then the other as the current alternates and do not have a chance to start turning. To get them started in the right direction, most single-phase induction motors have two sets of windings, a set for running and another set to help during startup. The start windings are spaced around the motor, so their magnetic poles are between the poles produced by the run windings. There are several types of single-phase induction motors using this basic arrangement. In a split-phase motor, the start winding uses many turns of wire that is finer than the wire used in the run winding. Because the start winding is more like a resistor and the run winding is more like an inductor, the currents in the start and run windings are out of phase with each other. Current to the motor has been split into two out-of-phase parts. Current in the start winding leads and produces its north pole before current gets going in the run winding. As a result, the stator poles rotate around the motor and pull the rotor around in one direction. Once the motor has come up nearly to full speed, a centrifugal switch cuts out the start winding. It is no longer needed and cannot stay connected because heat generated in its resistance would burn it out. You can recognize a split-phase motor by the two different gauges of wire in its windings and the presence of a centrifugal switch. In another variation of the split-phase idea, the start winding is wound with about the same gauge wire as the run winding, but it is fed through a capacitor. This provides a more complete phase shift of the current in the start winding and allows a more efficient start winding with less resistance. Starting torque is much higher. Again, a centrifugal switch cuts out the start winding and its capacitor when the motor comes up to speed. To provide an adequate phase shift, the capacitor used has a very high capacitance. In order to keep it a reasonable size, it is an electrolytic type, made for intermittent duty only. It would soon short out if left in the circuit, so the centrifugal switch has got to work. If you find a motor with a bad capacitor, do not just replace it without checking to see that the centrifugal switch is operating properly. There is no centrifugal switch in some motors. The start windings are permanently connected in series with a continuous duty oil-filled capacitor. These are called permanent split capacitor, or PSC motors. Their starting torque is much lower than capacitor start motors, but they are very simple and run smoothly and quietly. Still other single-phase motors use both an electrolytic and an oil-filled capacitor. These heavy-duty motors are usually called cap-start, cap-run motors. The capacitors are connected in parallel while the motor is starting up. A centrifugal switch cuts out the electrolytic start capacitor during run. Small light-duty AC motors use a shading coil to provide startup torque. A shading coil is simply a shorted turn or two of heavy wire around a part of the stator core. Startup torque and efficiency are both quite low. Even the best single-phase induction motors are generally less efficient and more likely to give problems than three-phase induction motors. When three-phase power is available, it nearly always makes good sense to use a three-phase motor. Now there is another completely different class of AC motors called universal motors. They look like DC motors with brushes, a commutator, and coils wound on the rotor. Actually, they are series-connected DC motors, but they will also run on AC, since the current reverses in both the field and the armature coils at the same time. The motor exerts continuous torque in one direction. Universal motors are frequently used in handheld power tools and household appliances like blenders and vacuum cleaners. Like series DC motors, they produce high torque at low speeds. Now let's take a look at one last type of AC motor that you may find. It is an induction motor, but it has rotor windings instead of a squirrel cage. It is used in situations where you want to be able to vary the speed and torque of a motor simply and dependably. Variable resistors are wired in series with the rotor windings. When their resistance is adjusted, rotor current changes, and so do the motor's torque and speed. Okay, we've seen how induction and synchronous AC motors operate. And we've seen the similarities and differences between three-phase and single-phase motors. You'll find more detail about the construction and operation of these motors in your study guide.